The 1918 Nobel Prize for Chemistry is probably the most important Nobel Prize ever awarded. It was given to German scientist Fritz Haber for solving one of the biggest problems humanity has ever faced. His invention was directly responsible for the lives of 4 billion people today. But when he received his prize, many of his peers refused to attend. Two other Nobel Prize winners rejected their awards in protest, and the New York Times wrote a scathing article about him. He was scientifically one of the most impactful and tragic scientists of all time. Perhaps more than any other single person, he has shaped the world we live in today. If you are an American citizen, you find an island with a lot of bird poop in it, well, you can claim that island for the U.S. and the U.S. will have your back. The president is authorized to send in the Navy and the Army to defend your newly discovered poop island, a covered island. There are currently 10 American islands that were claimed in this way. And even though the law that made this possible was passed in 1856, it is still in effect to this day. So why do people want poop-covered islands so badly? There are a few dozen islands off the coast of Peru, where millions of seabirds gather to mate, and the waters near the island are full of fish, and these millions of birds eat the fish, and then they poop. A lot. Since the region is hot and dry, this poop solidifies and accumulates over millennia. There are cliffs of bird poop, 30 meters or 100 feet high. And technically bird poop was called guano, and by the mid-1800s, buying and selling bird guano was big business. The price rose as high as $76 per pound, meaning you can trade 4 pounds of guano for 1 pound of gold. So why is there such a big market for bird poop? Well, to answer that, we have to look inside the human body. By weight, most of our bodies are made of oxygen, carbon, and hydrogen. The fourth most common element is nitrogen. Nitrogen is part of the amino acids that form proteins. It's part of hemoglobin, the compound that carries oxygen in red blood cells, and is the essential component of DNA and RNA. Nitrogen is essential for all life on Earth. We get our nitrogen by eating plants, or animals who have eaten plants, and the plants get their nitrogen from the soil. The same problem is that if you farm the same soil year after year, you harvest the nitrogen out of it. And eventually there isn't enough nitrogen for healthy plants to grow. They can't produce enough chlorophyll to photosynthesize which stunts their growth. Their leaves turn yellow and they are more susceptible to pests and disease. Crucially for farmers, nitrogen deficiency means smaller yields. The way to fix this is to add nitrogen back into the soil, which is where bird guano comes in. Guano is up to 20% nitrogen. Hundreds of years ago, Incan farmers realized that adding guano to the soil made their crops grow taller, this is what allowed them to grow food in places that were previously unfarmable and expand their empire. South America's rich deposits of bird poop didn't go unnoticed for the rest of the world. In 1865, Spain went to war against its former colonies of Peru, Chile, Ecuador, and Bolivia for control of the Guaran-laden islands. But such was the world's appetite for nitrogen that by 1872, guano was running out, and Peru banned further exports. The world would need another way to get its nitrogen fix. This was a crisis. William Crookes, a British chemist, made a dire prophecy in 1898 when the world's growing population and dwindling supply of nitrogen. He said, "We need to stand in deadly peril of not having enough to eat." In less than 30 years' time, he argued, people all over the world would be dying of starvation. But he also proposed a solution. It is the chemist who must come to the rescue. It is through the laboratory that starvation may ultimately be turned into plenty. Because here's the thing, nitrogen isn't rare, it's common. 78% of the air is nitrogen, but it is in a form that plants and animals can't use. Two atoms of nitrogen triple bonded together. This bond is one of the strongest in nature. The way to measure the strength of a chemical bond is by the amount of energy that is required to break it. So to break apart two chlorine atoms will take 2.5 electron volts. Two carbons require 3.8 eV. Two oxygens 5.2. But to break apart two atoms of nitrogen requires 9.8 electron volts, a tremendous amount of energy. Well, hold on. This is here. There are two processes that can do this naturally. Lightning releases so much energy that it breaks it apart into individual nitrogen oxides and quickly react. These molecules stay in the atmosphere until they react with water droplets in clouds and fall as rain. There are also few types of bacteria in soil that can break the N2 bond, using a tremendous amount of energy to do so. And they make nitrogen available for plants. But bacteria only replenish the nitrogen slowly, and there's not enough lightning to reduce nitrogen compounds at scale, so chemists tried. In 1811, whatever that name is, mixed nitrogen and hydrogen in a sealed flask trying to make ammonia, one of the nitrogen-containing molecules found in guano. When it didn't work, he submerged the flask 300 meters underwater to increase the pressure. And that didn't work either, but he was on the right track. Increasingly sophisticated versions of this experiment were carried out over the following 100 years, often failed. Don't mind if I drink some water. Okay, continue. So when Fritz Haber became interested in this problem in 1904, he was joining a long list of failed chemists. He was 36 years old, working as a low-level academic at the University of Karlsruhe. He also became a new father with a 2-year-old boy named Hermann and a wife, Clara. Who was one of the first women to get a PhD in chemistry. Driven by pride and not a competition with another scientist, Haber spent 5 years on the problem. His idea was to combine hydrogen and nitrogen not only at high pressure but also at high temperature. And in the presence of a catalyst, something that lowers the amount of energy required to split diatomic nitrogen. To do so, new experimental apparatus had to be invented. Haber worked tirelessly on the project, building equipment that could tolerate ever higher temperatures and pressures. He also got lucky. At the time, he was moonlighting as a technical consultant for a light bulb manufacturer. So there he had access to lots of real hard-to-find materials, like the element osmium. Osmium is rare. In his day, there are only about 100 kilograms of the refined metal in existence. But the company he worked for was experimenting with using it for filaments, so they would have most of the world's supply. Howard suspected it might make the perfect catalyst, so he brought a sample back to his lab. And there, in the third week of March 1909, He placed his sheet of osmium in a pressure chamber. There he pressured and heated the nitrogen and hydrogen to 2